All right, in this video, we are going to make sure that we know how to find the pH, pOH, hydroxide, and hydrogen concentration, as well as potentially solving for a Ka or Kb for the salt of a weak acid or a weak base, as we see right here in problems 5 and 6. So I'm going to recopy these guys, and we're going to try each one of them out. All right, the first one we're supposed to take a look at is this salt right here, sodium hypochlorite. Now, if you'll remember, we had hypochlorous acid a moment ago, and so we actually know the Ka value from that. So let's think about this salt. It's composed of two different ions, all right? It's got a sodium ion and a hypochlorite ion. Well, we have to consider which one of these is actually going to be doing anything in water. For example, if I had the sodium ion and I put it in water, would I expect it to reform sodium hydroxide? No. After all, sodium hydroxide is a strong base, and the first thing it's going to do is dissociate. So instead, I take a look at the hypochlorite ion in water. Now, when I put that in water, since hypochlorous acid is a weak acid, it's very probable that it will come together and form hypochlorous acid. So then, question, if that hydrogen came off of water and went on to hypochlorous acid, to the hypochlorite ion to make hypochlorous acid, what's left over? Well, once water loses a hydrogen, what's left is hydroxide. So the question is then, what kind of equilibrium expression am I interested in here? I just took this salt, put it in solution, and I am making hydroxide ions. So since I'm making hydroxide ions, that means I should be interested in the Kb. But I don't know the Kb, I know the Ka. But remember, we know that Kb times Ka should equal Kw. So we can use what we know, specifically the Ka, and solve for the Kb. These two numbers, when multiplied, should equal 1.0 times 10 to the negative 14. So when we do that, we take 1.0 times 10 to the negative 14th and divide by my Ka value, which is 3.5 times 10 to the negative 8, I end up with my Kb, which is 2.9 times 10 to the negative 7. That is my Kb value, and it's what I'm going to use to consider equilibrium. So I'm going to rewrite this equation right here, or actually maybe if this is my R, I'll just write my I, C, and E here. So my initial concentration of my OCl, well, basically when we're talking about a salt, we know that the entire thing dissociates. Sodium ions are incredibly soluble, so if we know the concentration of our salt, we know the concentration of each one of our ions since it's soluble. So we're going to start with the initial concentration of 0.00125. Again, we'll have no hypochlorous acid to start, and we'll have no hydroxide ions. But we expect to lose some of our acid or our hypochlorite ion here, and then gain some here and here. So we see the same setup that we've been seeing, but since this is forming hydroxide, we're going to set this, we're going to use the equilibrium expression Kb. So my two products, X and X, over my initial concentration. So X squared over 0.00125 minus X, which should be equal to my Kb, which I just solved for, 2.9 times 10 to the negative 7. So I solve for X, and when I do, I get 1.9 times 10 to the negative 5. So when I solve for X, what did I solve for? Well, let's take a look. All right, X is my acid concentration and my hydroxide concentration. Yes, I'm making some of this, but I'm making the hydroxide ion, and that's what's going to be affecting my pH. It's hydroxide ions and hydrogen ions that affect your pH. So what I just solved for was my hydroxide concentration. And using similar steps that we saw before, now that I know my OH concentration, I can find my pOH by basically taking the opposite log of that value. And so I should get 4.72. Similarly, that's going to be my pOH. I can solve for pH easily. So we know that pH plus pOH equals 14. So when we subtract here, we get the pH is equal to 9.28, which means then that this ion here was basic, which shouldn't be surprising. It came from the salt of a weak acid. The salt of a weak acid is a conjugate ion or conjugate base in solution. And so we're making hydroxide ions. It should be a base. Again, if I wanted to, I could totally find the hydrogen concentration simply by taking 10 to the negative pH, negative 9.28, and get my hydroxide my hydrogen concentration, which in this case would be. So what we just did is found the pH and all of its other values for what apparently was a weak acid. So we're going to do the same thing over here for this salt. Again, we have to figure out, do we know if it's an acid or a base? Well, take a look. We've got ammonium and we've got chloride. So if we think about it, what's going to happen when those guys go into solution? When I put NH4 plus in solution, it's very probable, since this has all 4 hydrogens on it, that it's going to donate a hydrogen. It comes from, in fact, it's going to end up making ammonia. These guys, this would be the conjugate acid and the base that goes with it. Now, if that's the case, if I just lost or gave my hydrogen, I gave it to my water, so I actually made a hydronium ion in solution. All right, same deal. What if I put chloride in solution? Hopefully we recognize that chloride is not going to actually steal a hydrogen and make HCl. It's not going to make a strong acid because strong acids cleave when they're in solution. So this is not going to have an effect on my pH because chloride is a terrible, terrible base. So since I formed hydronium ions, the value that I'm interested in is the Ka value. Now earlier I saw that the Kb value for ammonia was 1.8 times 10 to the negative 5th. So we could use that information to help us find the Ka. Again, the Ka is basically just the Kw divided by the Kb. So in our case, that's 1.0 times 10 to the negative 14th divided by our 1.8 times 10 to the negative 5, which ends up giving me 5.6 times 10 to the negative 10. Again, the reason it's so important that I'm working with Ka here is because I'm creating hydronium ions, so I know it's the Ka that I am interested in. So, that having been said, we can use this equation that's set up for us already as my R, and we can set up our R, C, and E. Again, it's really going to look exactly like what we've been seeing for all of these problems so far. We're going to see that my concentration here is 0.00125 because my salt dissociates into these 2 ions completely. That's what salts do when they dissolve. So the concentration is just like if I were talking about a strong acid or strong base. But I start with 0 of my ammonia, my conjugate base, and my acid. I know that I'm going to lose some of that salt ion, that ammonium ion, in the process of making ammonia and the hydroxide ion. So we have the same setup as before. So we should be able to set that equal to our Ka. 5.6 times 10 to the negative 10 is going to equal x squared over the quantity 0.00125 minus x. So solve for x and we get 8.4 times 10 to the negative 7. So the question is, when I solve for x, what did I actually solve for? Take a look. It's the concentration of these two things in solution. But this is going to be the species that affects pH. So I'm going to use that to find pH. So since my hydrogen concentration, or hydronium, same deal, is 8.4 times 10 to the negative 7, my pH is going to basically be the opposite log of that value, 8.4 times 10 to the negative 7. So I should get 6.07, or actually 6.08. That's the pH, so my pOH is just the difference with that and 14. So essentially I should be getting 7.92 there. And if I wanted to, I could totally find my hydroxide concentration. Not that I'm requested to, but the idea is that would just be 10 to the negative 7.92, which then would end up being 1.2 times 10 to the negative 8th. Hopefully this helped you with acid and base salts.